In this video, I'm going to wrap up section 5b with one more colligative property, which is osmotic pressure. And to begin with, let's talk about osmosis and how we can define that in terms of the chemical potential that we've been studying. So osmosis is the spontaneous passage of a pure solvent into a solution through a semi-permeable membrane. And a semi-permeable membrane is one that allows the solvent to pass through, but not the solute. So the solvent can pass through, solute can't. And now let's define the osmotic pressure, which uses the Greek letter capital pi. And osmotic pressure is the pressure that must be applied to the solution. So it's an external pressure applied to the solution to stop the influx of solvent. So whatever pressure is required to stop the influx of the solvent, to stop osmosis. So here's a diagram of a setup that illustrates osmotic pressure. So we have our semi-permeable membrane here in between the pure solvent and the solution. And the pure solvent and solution are each in a cylinder with a piston so that we can change the pressure on the solution. Over here, the pressure acting on the solvent is going to be the atmospheric pressure P. So the atmospheric pressure P is going to push down. And the osmotic pressure is the additional pressure beyond the atmospheric pressure that needs to be added over here in order to stop the solvent from traveling through the membrane. Okay, so that would be the amount of pressure that needs to be applied here is P plus pi. That's by definition of osmotic pressure. So with the osmotic pressure added on this side, then our two halves of this container are in equilibrium with each other. There's no longer a transfer from one to the other. So if they're in equilibrium, then we can express that using the chemical potential, which is what we've been doing in this chapter, and we're going to continue doing next chapter. So the chemical potential over here of the solvent must equal the chemical potential over here of the solvent. So remember, capital A is for solvent, capital B is for solute. So over here I have the chemical potential of the solvent. And solvent is all there is over here, actually. So this is a pure substance. There's only one component present. And this is the chemical potential at a pressure P. On this side, we still have the chemical potential of the solvent that we're interested in, but it's no longer, it no longer gets the star because it's no longer a pure substance. It's now in a solution with a solvent. And the pressure on this side is P plus pi. So in equilibrium, this chemical potential, mu A star at pressure P, is equal to this chemical potential, mu A, at pressure P plus pi. Okay, so if there's no more solvent moving into the solution, then these two halves are in equilibrium, which means that the chemical potential of the solvent, pure on the left at pressure P, is equal to the chemical potential of the solvent in solution at the pressure P plus pi on the right. So now we're interested in finding this pi, because the pi for which this equation is true is the osmotic pressure. Okay, so there's two things that make this solution on the right different than what we have on the left here. One is that it's at a different pressure. It has a different external pressure being applied to it. And the other is that this is pure, whereas this has a solute dissolved in it. And so I want to address both of those differences in regards to how they affect the chemical potential. So what is the effect of increasing the pressure on the chemical potential? So to answer that, we're going to look back to earlier in this section, 5b. Okay, I changed my mind about which one I'm going to address first. The first thing I'm going to address is the presence of the solute. How does that affect the chemical potential? And so we first saw that in 5a. For an ideal solution obeys Raoult's law, which is that the chemical potential of the solvent is equal to the chemical potential of the solvent in its pure form plus RT ln XA, where XA is the mole fraction of the solvent. And this natural log here is always negative because XA is always less than 1. If XA were equal to 1, then solvent is all that's present. And so we're back to the pure form. And in fact, it works out. ln 1 is 0, so this term goes away, and mu a equals mu a star if xa equals 1. 1 is as large as xa can get, but it can be less than 1. So in the case of a solution, xa will always be less than 1, which means that this term is always negative. So what we can conclude from that is that the presence of a solute decreases the chemical potential. Okay, so this was Raoult's law was on page 85 of my lecture notes, and I added this note that Raoult's law is a solution that obeys Raoult's law is called an ideal solution. And we saw earlier back in section 5a that this ideal solution assumption works well when the solution is dilute. And so we're going to come back to this diluteness assumption in a minute. Also from 5a, also from page 85, we developed a formula that tells us how the chemical potential varies as the pressure varies. And so that formula gives us the chemical potential of the solvent, assuming a liquid solvent, is equal to the chemical potential of the solvent in its pure form plus RT ln PA over PA star. And this equation was actually the predecessor to Raoult's law, because we observed that PA over PA star is roughly the mole fraction XA. And so if I replace that with XA, I recover Raoult's law. Okay, but before we did that, we had it in terms of pressure. And you can see what happens here if I increase the pressure on the solvent. Since natural log is a monotonically increasing function, meaning that its slope is always positive, then increasing the pressure is going to increase this quantity, which is going to increase the chemical potential of the solvent in solution. Okay, so since natural log is monotonically increasing function, then increasing PA is going to increase mu A. So let's look at these two results combined here and go back to this drawing here. So by adding a solute to the solvent over here, what we've done in comparison to mu A star is we have decreased the chemical potential by adding a solvent. But if we increase the pressure, then we can increase this chemical potential. So the solute decreases it, and then the pressure, by increasing the pressure, we can increase the chemical potential until it is once again equal to mu A star. Okay, and then that is what the osmotic pressure is how much pressure do we have to apply here to increase mu A to compensate for the fact that we decreased it by adding a solute. All right, now we're ready to start looking for pi and how we can solve for pi. And we're going to use two equations here. We're going to use this equilibrium condition that I established above next to the drawing. And this is, you could take this as the definition of the osmotic pressure. So we're going to take that formula and Raoult's law. Okay, so these are our two equations. And just to be clear, let me include the pressure over here in Raoult's law. So we're talking about mu A at a pressure P plus pi is equal to mu A star at pressure P plus pi plus this RT ln XA term. Okay, now what I'm going to do is I'm going to take this formula for mu A P plus pi, and I'm going to plug it in up here. So effectively what I'm doing is I'm equating these two equations. The left-hand side here is equal to the right-hand side here. So mu A star at a pressure P is equal to the right-hand side over here. And now I'm going to solve this for mu A star at the elevated pressure P plus pi. Okay, so I solved the previous equation for mu A star at the elevated pressure, and I get this expression. I'm going to label this one with an asterisk because we're going to come back to it in a minute. So I want to make an observation about mu A star. This is the chemical potential of a pure substance. And remember, when we first saw chemical potential, it was for only pure substances. And for a pure substance, we've seen that the chemical potential is equal to the molar Gibbs energy, the Gibbs energy per mole. So this is true for pure substance. And here we have a pure substance. So if I want to know the result of this increase in pressure on mu A, I'm going to go back all the way to section 3E and find a formula that involves the change in the molar Gibbs energy as a result of changing the pressure. Okay, so that's from page 58 in the lecture notes. That was a while ago. And that formula is that the molar Gibbs energy at the final pressure is equal to the molar Gibbs energy at the initial pressure plus Vm times delta P. So final pressure minus initial pressure. And just a quick note, you can go back to page 58 to see this in more detail. But in order to arrive at this, there was an integral where we pulled the molar volume out. So to do that, we assume that the molar volume is constant over this pressure range, Pi to Pf. And we call that the incompressible assumption, which we discussed is a good approximation for solids and liquids. It's not a good approximation for a gas. But we're dealing with a liquid here. We're dealing with a liquid solvent. So we're going to use this incompressible approximation because it's a good approximation. Okay, now using this, the initial pressure is P, and the final pressure is P plus pi, and we want to know what happens. So Gm at the final pressure, P plus pi, equals Gm at the initial pressure, which is P, plus Vm times P final minus P initial. Well, P final minus P initial is just going to be pi. And now I'm going to write this in terms of mu. Remember, Gm and mu are the same thing. Okay, so I'm going to write this in terms of mu. We're dealing with a pure substance here. That's why we're allowed to use this. So I'm going to write mu A star P plus pi equals mu A star P plus pi times Vm. All right, and now here's where I'm going to go back and use this formula that I labeled star, because I have a formula here for mu A star P plus pi. That's my left-hand side right here. So the left-hand side of this is equal to this. So now let me put that together, and we get, all right, so this is what we get. And notice that the mu A star cancels on each side. And I can write this as negative RT ln XA is equal to pi times Vm. Okay, we're getting very close to being able to solve for pi here. We're going to make a few substitutions and approximations to really simplify this. First of all, this is a binary mixture. We just have one solute and one solvent. So there's two components in this mixture. And therefore, XA, the mole fraction, is equal to 1 minus XB, the mole fraction of B. Okay. That is to say that XA plus XB equals 1, because if there's only two substances, then the two of them together must account for 100% of the moles that are present. So if I make that substitution in here, then I get 1 minus XB. Okay, and for the left-hand side. And here I'm going to use what I mentioned before, since we're using Raoult's law. And Raoult's law is a good approximation when we have a dilute solution. A dilute solution would have very little, a very small percent of its moles would come from the solute. Okay, so that means that this XB is much less than 1 because it's dilute. And we saw this before as well. If I expand ln 1 plus x into a Taylor series, I see that it's approximately equal to x when x is small. That is x much less than 1. Okay, and that's exactly what we have here, except x is going to be negative xb. So using that, I can approximate this 1 minus xb, ln of 1 minus xb, as just negative xb. And so the negative and the negative xb is going to cancel this negative, so I get RT xb. Okay, this is my left-hand side. All right, and now let's equate that to the right-hand side. So we have RT xb is equal to pi Vm. Okay, now, what is xb? The definition of xb is the number of moles of B over the total number of moles, which in this case it's a binary mixture, so that's just Na plus Nb. And again, we're going to use the dilute approximation and say that this is approximately equal to Na, because Nb is much less than 1. Therefore, Na is very close to 1. So 1 plus something very small. So it's going to approximately be equal to Na. Okay, again, this is because it's dilute. And so we have Nb over Na. And I'm going to make that substitution over here and move things around just a little bit. I'm going to move the Na over to the right-hand side. Okay, so making that substitution and rearrangement, I have this. And I'd like to focus on this Vm times Na term right here. So Vm, the definition of Vm is the volume per mole, so that's the total volume, divided by the total number of moles. And again, I have Na plus Nb in the denominator. I'm going to approximate this with Na because it's dilute. So Nb is very small compared to Na. And therefore, this is V over Na. And with that approximation, you see that when I put V over Na right here, the Na and the 1 over Na are going to cancel. So I end up with RT Nb equals V pi. Just to rewind real quick, as I was explaining that last part, I realized I misspoke back here. I was talking about this being close to 1 and this being close to 0, I was thinking about mole fractions. That's not a proper explanation. However, this is all still true, that Na plus Nb is approximately Na, because Nb is very small compared to Na because it's dilute, okay? And that's the same approximation that I made here. Okay, now if I divide the V over, I have this Nb over V term. Let's take a look at that. So this is the number of moles of solute divided by the total volume of the solution. So this probably looks familiar to you. This moles of solute per volume of solution is called the concentration. Okay, so in fact, in particular, this is the concentration of substance B, our solute, our only solute in this case. So this is the concentration of B here, NB over V. And so now I'm going to write down my equation for pi. It's equal to R times T times the concentration of B. Okay, so after numerous substitutions and a lot of simplifications because of the dilute approximation, we arrive at this equation. And this equation is called the Van 't Hoff equation. And remember, in getting to this equation, we assumed that it was, so this is valid for ideal solutions that are dilute. So I'm going to call that ideal dilute solutions. Okay, now how about non-ideal, aka real solutions? So we're going to do like we did before when we were looking at the equation of state of gases. One of our equation of states was the virial equation of state, and what we did there is we assume, so we're going to use this process here, where we assume that this here is the first term in a power series expansion. And so we're going to add the other terms, and the other terms are going to be multiplied by increasing powers of the concentration. Okay, so let me write that down. Okay, so pi is equal to RT, and we're going to change the solute letter to J so that we don't confuse it with the coefficient B here in a second. You'll see what I mean. And so we're going to multiply this by 1 plus, this is where we put our power series. So the first element in our power series is the concentration to the 0th power plus some coefficient times the concentration to the first power plus some coefficient times the concentration to the second power, and so on. Okay, so this is why we changed the B to a J so we don't confuse it with this B right here. Okay, so we renamed the solute to J so as not to confuse it with virial coefficient B. And this virial coefficient B has its own name. It's the osmotic virial coefficient. And C is another coefficient, and there's a D and so on. But to keep things simple, typically we truncate this power series before we get to the nonlinear terms. Okay, so we're going to do that now. So we're going to truncate the nonlinear terms from the power series. Okay, although this is technically a square of J, but I'm just focused on this inside the parentheses. We're going to cut it off after Bj. Okay, so pi then is equal to RT concentration of J times 1 plus B times concentration of J. Okay, now I'm going to divide this concentration of J over here, and we'll see why we're doing that in just a minute. And then I'm going to go ahead and expand this binomial here. So I have RT times 1 plus RT times B times the concentration of J. Okay, and to give you an idea of why we did this, what we'll be doing here in a minute is we're going to treat this quantity over here, call it Y, pi over the concentration, we'll call that Y. The concentration itself we call X. And so if you look at this, this is the formula for a straight line. If we're plotting pi over concentration versus the concentration, we should get a straight line. And the straight line has this for its y-intercept, RT, and it has this, RTB, for its slope. Okay, this equation is going to be useful in just a second, so I'm going to go ahead and label it star star. And now we're ready, now that we have that equation, we're ready to talk about osmometry. So what is osmometry? Osmometry is the method for, it's a method for determining the molar mass of a solute by measuring the osmotic pressure. And often in laboratories, this solute is some macromolecule that you want to measure the molar mass of. Okay, so we'll go through an example. There's a table of data in your book, so this would be like sample data from a laboratory measurement. And the table gives us two quantities: C mass of the solute and pi, the osmotic pressure. C mass is the mass concentration of the solute, okay, otherwise known as density. It's the mass of solute per volume of solution. Okay, so our data in the table is in grams per cubic decimeter. And then pi, of course, osmotic pressure, and it's in units of pascals. Okay, I want to use our prior equation, star star, but that equation was in terms of the concentration, not the mass concentration of J. So let's look at the relationship between those. So the molar mass is the mass per mole, and therefore, if I take the mass concentration and divide it by the molar mass, what do I get? Well, mass concentration is mass per volume, right? It's a density, effectively. And M is mass per mole. And you see that the masses cancel. And this 1 over moles is going to come up top. And so I get moles per volume. Okay, so this is moles of J per volume of solution. And that's equal to concentration J. Okay, so now we have a way to relate the concentration to the mass concentration. So we're going to go back to equation star star. And I'm going to make this substitution. I'm going to take the J, the concentration, and replace it with this fraction. Okay, so I've rewritten star star here. And now I'm going to make this substitution for J. So on the left, I have pi over the concentration of J. So that's going to be pi over the mass concentration of J times the molar mass is equal to RT plus RTB times concentration of J is mass concentration of J over the molar mass. Okay, now I'm going to divide by M, and I get pi over mass concentration, Okay, so this left-hand side looks a lot like the left-hand side that I had up here, right? Pi over concentration, now it's pi over mass concentration. And to do that, I had to divide by m everywhere here. So this first term is RT over m. And the second term is RTB over m squared times C mass. And now we can do what I was mentioning before. I call this Y. I call this X. Okay, this is exactly like we had before, except it's mass concentration instead of concentration, moles per volume. It's mass per volume instead of moles per volume, but it's the same idea. These coefficients have changed a little bit, so this is still the slope, and this is still the y-intercept. And so what we do is we take our data, so we have pi, we have C mass data, and we're going to plot pi over C mass versus C mass, okay? And when we do that plot, we can look at the y-intercept here, and we're going to use this to find m, the molar mass, because here there's an m in our formula here. R and T are known, and so when we find the y-intercept of our data, when we plot it, we can solve for m. And then once we know m, then we can use this formula, equate it to the slope of our line that we plotted, and now I know m and r and t, so I can use this formula then to find the osmotic virial coefficient B. Okay, so this is the experimental procedure, or the procedure that we do on the experimental data in order to find M and B. Okay, so let me write down some data and we'll do it real quick. Okay, so here's a little data table. I have C mass, which is in grams per decimeter cubed. And then I have pi over C mass, which has a weird unit. It's pascals, decimeters cubed over grams. We'll sort all the units out here in just a minute. And these are the values here. So what I'm going to do is I'm going to plot each of these points. This is y1, x1. And this is y2, x2, y3, x3, and so on. So I'm going to plot these points. And then I'm going to use linear regression. And for example, the least squares method. So linear regression fits a straight line to this data. And when we use linear regression, we get a formula, y equals mx plus b, for the line that best fits this data. Okay, so using that data and using linear regression, we can find that the y-intercept is 19.8. And going back to this, the y-intercept was equal to RT over M. So 19.8. So RT over M equals 19.8. What are the units? Well, the units of RT over M here must be the same as the units of this, pi over C mass. And we already determined that those units were pascals, decimeters cubed over grams. So this is pascals, decimeters cubed over grams. All right, and now we can solve for M, because our goal was to find the molar mass of some macromolecule. And so we get RT over 19.8. Now let me plug in some numbers. The lab temperature when this data was taken was 298 Kelvin. So I have R times 298 Kelvin. And this, I'm going to convert the decimeters cubed into meters cubed. So since there's 10 decimeters in a meter, then there's 1,000 decimeters cubed, and a meter cubed, so times 10 to the minus 3, I have to divide by 1,000. Pascals over grams times meters cubed. Okay, and so now let's work out these units. So first and most obviously, the Kelvin cancel. And here I've got joules in the numerator and I have pascals in the denominator. Let's take a look at that. So 1 joule is equal to a Newton times a meter. A Newton is a kilogram meter per second squared. So 1 joule is a kilogram meter squared per second squared. And pascals are force per area. So that's going to be a Newton, kilograms meters per second squared, divided by an area, divided by meters squared. So I end up with kilograms over second squared meters, because there's a meter and meters in the numerator and inside the Newton, and a meter squared in the denominator because of the area. So I end up with 1 over meters. And then if I take these two together and I find what is joules over pascals, we see that the kilograms cancel and the second squared cancel. And I have meters squared divided by 1 over meters. That's meters squared times meters, or meters cubed. So up here, this joule over Pascal is going to give me a meters cubed in the numerator, and that meters cubed is going to cancel this meters cubed in the denominator. So this joules, pascals, and meters cubed all cancel. And so what I'm left with is 1 over moles divided by 1 over grams. So that's grams per mole. All right, so plugging these numbers into a calculator, I end up with 1.25 times 10 to the 5th grams per mole, or 125 kilograms per mole. So this is the molar mass of this unknown macromolecule. And now that we know M, we can go back and we can find the osmotic virial coefficient B as well. Okay, so this process is called osmometry.